Okay. So yeah, thank you, Dr. Bouchard. So whenever you are ready, please go ahead and present to us. Thank you very much.
Awesome. Yep. Well, yeah, Rudra, thank you for inviting me. It's always great to talk to the Frontiers camp. I'll give a quick introduction to myself and kind of set the tone as to why I'm talking to you today, and then we'll get into the actual research. So yeah, as Rudra said, I did my PhD at WPI. I also did my undergrad and my master's degree at WPI. So I started in 2015 was when I first came to WPI, and I did not leave there until December of 2023. So kind of a long time to spend at one university, but I really enjoyed it. Hopefully you guys are all seeing the same things that I saw about the campus. It's beautiful. There's a lot of great people there, a lot of really cool opportunities. After leaving WPI, I went directly from my PhD into a postdoc, which is a pseudo employment type thing. I'm on a fellowship right now with the United States Naval Research Laboratory down here in Washington, D.C. We've got a pretty cool location. We're right on the Potomac River. I can step out of my lab and look to my right, and I will see Congress, and I can see the Washington Monument. Really cool area. You guys should definitely come down and check it out. Sometimes we'll have like open days to the public. The research that we're doing down here, you probably heard a little bit about when you took the tour of LEAP the other day. We work in integrated optics and integrated photonics. And specifically, this talk is about some work that we were doing on so-called free space optical communications. And I'll describe that a little bit more in depth when we get into it. I'm not super used to giving presentations like this virtually, so we're going to have to kind of work together on how this works. But the way that I usually like to give these types of presentations is, if at any point someone has a question, please let me know. I would rather stop and like address the question. It usually makes for a much better presentation overall because I can address things as they come up. So Rudra, if you,
Jack,
yep.
Jack, let's do this. This presentation. I mean, at 10:25, we need to go out of this room. So please
Okay.
continue presentation and all the question Q&A towards the end.
Okay, that sounds good to me.
Thank you very much.
Yep. Cool. All right. So without further ado, I will turn on my little virtual laser pointer and get started. So yep, I'm Jacob Bouchard. I'm presenting to you today on my work on advancing free space optical communications, integrated optical beam steering at the U.S. Naval Research Laboratory. And these are all the great people that I had an opportunity to work with while working on this program. So I'm going to start by first giving a background in what integrated photonics are. Some of you may be familiar with what integrated circuits are, integrated electrical circuits, and sort of the path that went on. So back in the 1910s, 1920s, we had these large electronic components, these individual discrete components, things like vacuum tubes, magnetic amplifiers, large singular transistors, and these components were really bulky. A computer would take up the size of a large room, and it was very hard to get any sort of like dense computing architecture when we got there. Moving to integrated electrical circuits, where we're sort of making these as a whole bulk device with hundreds, millions of transistors all in a small package. That is what is given birth to the current technological age that we're in, where you can have a computer hundreds of times more powerful than those that sent humans to the moon and back. You can have a computer way more powerful than that just in your pocket. Well, we're trying to do a similar thing in photonics with optical components. So out there exists, you've probably walked into some optical laboratories over the past few days walking around WPI, and I'm sure you'll see some more, where you see these really complicated systems set up on benchtop optical tables. They take up, again, like an entire room, and there are these mirrors and lasers and either like free space beam paths or things like optical fibers. You get things like electro-optic modulators and spatial light modulators, and they're these giant, huge, discrete components that you would never be able to fit in your pocket. Well, we're trying to do the same thing that they did in electronics with these optical components by making them these large monolithic devices, or these small monolithic devices in integrated photonic circuits. So this will allow us to do compact things like optical computing, optical interconnects. This is being investigated as a platform for quantum computing. There's also applications to far more efficient AI calculations and all these other things. It's a really big deal. There's quite a bit of investment, and it seems like every time that the government does a set of interest items, photonics keeps popping up more and more. So I'm sure we'll be hearing about it more in the news as time goes on. I'll show more of these photonic integrated circuits. So if any of you have ever seen integrated electrical circuits, you'll see they're made on these large silicon wafers. We're doing the same thing for integrated optics. We're actually using the same, if not similar, foundries to manufacture them. These are these massive clean room facilities that they're able to take these 12-inch in diameter silicon wafers and do what's called photolithography, where they are patterning a whole bunch of different layers of different materials to build our waveguides and our modulators and all these other discrete components that we have on chip. So, just to give an idea of the scale here, we go from a 12-inch or 300 millimeter silicon wafer. We have our individual printed circuits on here. A single one of these chips is about, we can see about the quarter of a size of a $quarter, about 2 to 8 millimeters on a side. Within this chip, there's a whole bunch of subsystems, and the size of the subsystems are about 0.5 millimeter to 2 millimeter on a side. So they're quite small. And then we can get down to the resolution of singular components being on the order of 10 to 200 microns. And to give some context here, a human hair is about 75 microns in width. So we can get components. We work on singular components that are smaller overall. They have a smaller footprint than the thickness of a human hair. So we can get really, really precise with these things. We're making these absolutely minuscule components quite repeatable and quite accurately, which is pretty cool to work with. I'll just give a quick overview. This is a standard slide that we include, just showing silicon photonics foundries all over the world, different technologies that people work on. You might see some names here that you recognize. Obviously, Intel is a pretty big one, but a lot of these foundries are, manufacturing both optics and electronic circuits. The foundry, the only reason really why I include this slide is just to point out the foundry that we work with primarily is AIM Photonics. They're based out of Rochester, New York. They've got a pretty large clean room facility up there. They do the manufacturing from bare silicon wafer all the way out to like fully packaged devices. It's a really neat facility up there. Again, sometimes they'll do these public openings that you can go up and tour the facility. There's a lot of openings up there for interns. So throughout this talk, I'll be plugging different ways that you guys can get involved in this ecosystem now when you're in college doing your undergrad degree, or if you go on to graduate school, ways to also engage. All right. So I talked a lot about the high-level overview. Let's start getting a little bit more granular. The way that if you are a researcher or someone that's wanting to create an integrated photonic circuit, the way that you interface with foundries like AIM Photonics is by using a multi-project wafer run, or an MPW. You'll probably hear me mention it a few times throughout the talk. The way that they do this is they subdivide that huge 300 millimeter wide silicon wafer into a bunch of smaller areas that you can buy, like a small piece of real estate on that huge wafer. To put it in context, if you were to buy the full wafer, I think it's close to $1 million to get one run done. One of these small MPW tiles costs around $150,000, depending on the technology you're getting run. So still expensive, but it's an order of magnitude less expensive. It's a way for smaller businesses and individual research labs to get involved on designing and getting back some of their own material. AIM Photonics offers a bunch of different technologies on their different MPWs. That I gave an example here of. There's their low loss active pick, and this is a side view, sort of giving an idea of all the different layers that they can put down. So each one of these layers is a different photolithography step. They're depositing things like in gray here, these are silicon waveguides. These are good for infrared light, so non-visible things that are typically used for standard telecom. So things like your Verizon Fios that you might get fiber optic internet over is all carried on infrared light. In red here, we have silicon nitride waveguides, which are a newer material, which is better for visible light. Visible light is more promising for things like quantum computing, because there's a lot of interesting atomic transitions that happen in the visible or near visible. They can put down these active components like germanium photodiodes. We get all these different metallic interconnects, so we can create electronic circuits on the chips as well. We can do these weird trenching things where we can actually cut into the silicon wafer and create these trenches in our silicon oxide. So that's what this blue here is, silicon dioxide, which is just glass. We can create trenches in that, and I will go into a little bit more detail on why we would want to do something like that a little bit later. And then another option that they have are these passive picks, which are much more simple. We don't get all of these fancy active layers. We just get some silicon nitride, and a trench that you can go down to interface with some of the silicon nitride. This is just to give a sort of a background on how we're actually manufacturing some of this, and also the different materials we're working with. All right, moving on to the actual project that I'm presenting today, the free space optical communication. I want to give a background on what that is. So you're familiar with things like radio frequency communications. You know, you have a walkie-talkie and you can communicate with somebody else. If they're tuned into the same station as you, you can communicate. And the Navy uses things like this. They use their radios to communicate ship to ship, but it's not a secure method of communication, because when you're sending out those radio waves, they're going in 360 degrees and they're propagating all the way around. And if there's somebody else in the area, they can listen in on what you're talking about. And you need to devise all these different codes and encryptions and things like that. Another system that is in use is free space optical communication, whereby you encode your message on a laser beam and send it just through the atmosphere to whoever you're trying to communicate with. This is far more secure because it is very highly directional. You know, the laser doesn't really diverge that much. You're communicating over a spot that is a few millimeters wide rather than over the entirety of the horizon. And it's also really easy to tell when someone has intercepted your message, because they literally have to come between you and who you're communicating with. So they have to stick a receiver in the beam path, and it's immediately obvious that your communication has now been compromised and someone's listening in. So this is actually pictures off of the deck of a ship showing a free space optical communication setup. So it's this large gimbaled laser and mirror. They can sweep it around and point it. These systems work really well on ship-to-ship communication and ground-to-ship communication and things like that. But we run into a problem when we want to make these systems smaller. You know, these large gimbaled things obviously weigh quite a bit, and if we want to fly it on like a plane or something like that, it's not going to be as practical. It's going to weigh too much. So we wanted to look at a way to use our the group here does a lot of integrated photonics. We wanted to see if we could use integrated photonics to solve this problem in a different way. If we could do a way to steer an optical beam without any moving parts. And we looked into what's called an optical phased array. And I will talk about that and sort of how we design that. This is just to give sort of the metrics we were trying to hit. So a device like an optical phased array would have to be something that would use a small amount of power. We want to have fast, stable, and wide steering to be able to compete with these mechanical beam steers. So about 45 degrees field of view is what we're targeting. We want to be able to scale it to a bunch of channels, and it needs to be something that is compatible with one of those MPW foundry processes that we showed before. That way, if the Navy is actually interested, they're not going to want one or two, they're going to want tens of thousands of them. So it needs to be something that can be mass producible. So we went ahead and actually designed this. This is the image up here is a microscope picture of a 8-channel optical phased array that we designed in-house. These are they're built to scan in 1 dimension, so that's why I call it a 1D integrated optical phased array. Essentially, all this is we have a laser input somewhere off to this end of the device. These are all like planar waveguides. The laser travels along these dark lines here. This is the waveguide itself, and it splits. Here is a splitter tree that splits the signal from 1 channel to then 2 channels to 4 channels, and then back behind this electrical routing, it splits into 8 channels finally. The light then propagates across these 8 channels and goes into our thermo-optic phase shifters. So we have 2 sets of those, one to scan in one direction, one to scan in the other direction. And then it propagates out to the edge of the chip, which is here, and goes off into free space. Now, we end with 8 individual channels, but they're spaced such that once they go out into free space, they are close enough together that they interfere with each other and create a multi-slit interference pattern, which is shown down here. So we get, instead of 8 individual bright spots, we get 1 really big bright spot of constructive interference. And then off to the sides, we get some dark spots of destructive interference. And then way out, depending on our spacing, we'll get these degenerate, we call them degenerate side lobes, but they're really just extra spaces of constructive interference. So some of our power gets thrown off into these little extra stubs. They're undesirable and we don't really want them to appear at all, but it's sort of a limitation of some of these designs that they're going to be there somewhere. There's a calculation that we can do on figuring out where they're going to be based on the spacing of these channels, and we'll talk about that in just a little bit. This one was designed on the active MPW, so we were able to do our thermo-optic phase shifting, which I think I've got a slide on that. I'm going to go back just a moment. We're able to actually heat the waveguides up in these thermo-optic phase shifters. We have resistive heaters here, and that's what changes our phase and lets us steer the beam. Now, I mentioned the multi-slit interference. I think that's a college freshman physics topic, so I will go in and describe that a little bit more to make sure that everyone's on the same page here. I apologize if this is old news or if I'm not explaining it in the way that you're used to seeing it, but for these optical phased arrays, we can think of our discrete emitters. Right here, I only have 4, but we in practice we have 8, but it all works the same way. We have 8 slits. They are spaced at a pitch, some known pitch, or in our equation you'll see it show up as D. And in this case, this is our unsteered case. Our incoming light hits our multiple slits, and the phase of the light across all of these slits when it hits is consistent. They're all the same phase. So we wind up with most of our power concentrated in the 0-degree lobe. So it's centered on the slits. Then we get these side lobes like I talked about, and the power, if we integrate over the whole power spectrum, we'll get sort of a Gaussian beam distribution here. So So that's our far field diffraction pattern. Most of our power is in the center, and it falls off towards the sides. When we go to actually steer this, though, like I said, we have these thermo-optic phase shifters that change the phase across each one of our emitters, or our output waveguides. So we'll say in this case, there's phase 1, phase 2, phase 3, and phase 4 across our 4 outputs. And these have some linear relationship whereby phase 1 is equal to phase 2 minus some constant c, which is equal to phase 3 minus 2 times c, which is equal to phase 4, which is minus 3 times that constant. So it's all offset by some linear offset. And when we do that, we see that our power in the far field is no longer centered on the array. It's moved. So that interference, because of the phases, it shifts where our power comes out, and we get a quote-unquote steered beam. We've steered our power off to some known angle. That's pretty cool. The basic physics tells us that this should work. So we have our phase shifters, we have our multiple emitters, and we're now at the point where we can start testing it. I want to go in for just a minute and show what these thermo-optic phase shifters actually look like. What you're looking at here, this is the so-called GDS layout. This is what, when we design these circuits, this is what we submit to the foundries for fabrication. And it's sort of just like a drawing that we do in a bunch of different layers that they then interpret into the actual circuit that they make. So like I said, our thermo-optic phase shifters, they're actually, it's like a long resistor that we draw out. And we contact down with metal, and we get a current across that resistor, which heats up our waveguides. And if we look, the length of our resistor changes as we go across our 8 waveguides. That length change is what gives us a linear phase relationship between these 8 emitters. We wanted to see sort of the sort of power we could expect from a thermo-optic phase shifter like this. So we used a physics simulation software called COMSOL to analyze the heat profile we would get from a thermo-optic phase shifter like that. And we see that for applied electrical power of about 35 milliwatts, we get a change in the temperature here of about 16 degrees Celsius, which seems fine. The thermo-optic coefficient of silicon, which is what makes it change its refractive index and thus the phase of the wave based on temperature, is pretty high. So 16 degrees should be good to get some modest steering out of this array. Like I said, we had this fabricated, so this is just a more zoomed in view of that microscope picture. Also comparing it to the GDS, we can see that what we asked to be manufactured is what they did, and it looks great. You can see the resistive heater here has a slightly different color than the waveguides, and these bright spots are the copper metal wire tracings. We've got 2 phase shifters, one for positive and one for negative steering, or both directions that we're steering in. Now comes to the lab side of things. How do we actually measure these to make sure that they work now that we've got them in hand? Here we can do so-called direct imaging, where we take our optical phased array, put the output of it into a microscope objective, direct that onto some imaging lens and then an infrared camera, and we get a direct image of the emitters, the individual emitters of our optical phased array. You might see that this is a lot more than 8 emitters. Each one of these dots is a discrete emitter. This is a spoiler for the next part of further on in the presentation, where we make more channels on these arrays. But so this is 32 channels. But for their 8-channel ones, you'd only see 8 bright spots there. Now, that doesn't tell us how good our steering is. Even if we apply a phase change, we're not going to see these emitters change. So what we need to do is we need to look at the far field pattern. And we do that by putting in an extra positive lens, which some people call a Fourier lens in these systems. And that gives us a Fourier image or a far field diffraction image. This looks a whole lot different than what we were seeing before. These are a bunch of vertical stripes. And what this is actually the that diffraction pattern that we talked about before, where this stripe here is our primary power lobe, and then off to the sides are all of these degenerate side lobes that we get. I think it's pretty cool. If we track where that central lobe is, we can see how our steering's doing, and it should give us an idea of the efficiency of our optical phased array. So let's zoom in a little bit on one of these images. Here's our 8-channel OPA that we had talked about before. The spacing between our central lobe here and our first order degenerate side lobes is about 22 degrees. Now, I mentioned before that we really don't like having these lobes here, and one of the reasons for that is they're a fundamental limit of how much we can steer our array. We can't steer our central beam past the position of our first order side lobes in either direction. So that limits our total steering to about 45 degrees, which, if you remember earlier on in the talk, I said that was about our target for a field of view, which, cool, looks like our phased array should actually work for what we want to do. And this is our pitch, or our spacing of our channels, was about 4 microns. So the pitch is usually what sets that spacing of main lobe and side lobes. Now, here's a little movie of me applying a whole bunch of power to this thing and looking for the steering of that main lobe. So you should see it move to the left in this video. I don't know about you guys, but I don't really see this moving very much at all. And I'm going up to 90 milliwatts, which for a device the size of, I think it's 150 square microns, that's a whole lot of power. That's a really high power density. So something's not going right. If we graph our heating versus our steering versus our power, we see that we really only get 2 degrees of a field of view, or 1 degree in one direction and 1 degree in the other direction, for power applied all the way up to 90 milliwatts. That gives us an overall steering efficiency of 0.01 degrees per milliwatt. That's really bad. That's not going to get us to a working device. And the reason why that happens is because we're losing most of our heat that we're putting into our device. It is just escaping right to the silicon substrate. It's a great thermal pathway, and all the heat's just going right out of it. This is where I showed you a little bit earlier. We can actually start etching out that silicon substrate, and that should give us a better device. It breaks that thermal pathway, and it isolates our thermal structures, so we decided to try it out. We manufactured a new set of these 8-channel optical phased arrays, where we just opened up these 2 trench openings and then etched out the material from underneath of our thermal optic phase shifters. You can actually see in this image up here, there's sort of a darker color up here and down the waveguide. That's this whole area is suspended. It's just a little glass bridge over nothing. We simulated what this would look like and saw that for the same 35 milliwatts as before, instead of a 16 degree temperature change, we would get 1200 degree temperature change. And for context, silicon, which this is made out of, melts at 1100 C. So if we apply 35 milliwatts, this thing will explode. And we have seen them explode in the lab if we give them too much power. I will say that this slide contains, again, a spoiler for a little bit further on, and that spoiler is in this image. I won't mention what it is, but try to remember what this looks like. Yeah, so we get a 9 times efficiency increase with this isolation trench. So cool. Let's see what we get. Here's that same video, but with a trenched one, and hopefully you're seeing that main lobe is actually steering. It's moving. It's really cool, and we're only applying under 20 milliwatts because we don't want it to explode. I think this image, yeah, this video goes up to like 19 milliwatts. Really cool. We're still not getting to our maximum steering of 45 degrees though, and we get about 6 degrees of steering, full field of view for less than 20 milliwatts of power. We get an order of magnitude increase in our efficiency, so 0.14 rather than 0.012. And we get an increase in steering efficiency of 13 times. That's awesome. But again, 6 degrees is not 45 degrees, so something is still wrong here. And that problem is really well illustrated by these two images here. For this array, if we apply a modest amount of power, we get a beam that is steered, and we still get a nice, bright, discernible line. When we start getting up to higher powers, though, that line smears out, and most of our power is being distributed across a pretty wide angular swath. So that's our beam is smearing out. I mentioned before that I had a spoiler for that, and here's that image again. What happened to our nice triangular heat pattern that applied a linear phase ramp? Well, it's gone. Now that we've broken our main heat path, yeah, it should look like a triangle. It doesn't anymore. All of our heat is just equalizing across all these waveguides because it's got nowhere to go. So we don't get a linear phase ramp anymore. That's a problem. We decided to move on, and we scaled up the channel number, and we figured that a way to keep that linear phase relationship preserved was to isolate each waveguide individually. So before, if you remember, we isolated that whole thermo-optic phase shifter as one bulk component. Here we're isolating each individual thermo-optic phase shifter as a discrete thing. So we get sort of this net-looking type thing. Each one of these rows is separating a heater in a 32-channel optical phased array, and here's what the whole component looks like, so much larger. The only problem with doing this inter-channel isolation is that the spacing of our channels is now pushed out to 15 degrees, where in the 8-channel OPA, we had a spacing of about 4 degrees. So this is a 3 times increase in pitch, which is going to degrade. Those side lobes are going to move really close in, and we're going to not have as wide of a total steering. What we see when we graph our steering versus power is we get a field of view of almost, it's plus or minus 10, so it's almost 20 degrees field of view for less than 100 milliwatts. We see that same pretty decent efficiency in steering of 0.1 degrees per milliwatt, and we don't degrade our beam when we move to higher steering powers. But that 12 micron array pitch is limiting our performance. 20 degrees is still not 45 degrees, so it's not super useful. I want to give a shout out to one of my colleagues, Nathan Tyndall, who helped me with the layout of all of this, but we thought, why don't we just come out of our thermo-optic phase shifters and then squeeze the waveguides back together. And that's exactly what we did. We just squashed them together. And we have these little bumps in here because when we go to squash them together, some of these waveguides are longer than others, and we need to make sure that the light traveling through the waveguides all travel the same length. So we make these little compensation bumps so that even though these inner waveguides aren't really moving when we do this tapering, they still travel the same length. Here's where I have to throw something out, which is a little sad. Our samples that we have in hand that we were able to measure for this project don't actually have that thermal isolation, which limits our steering, but we can look at the non-steered patterns of these and see that we do get, there is some effect that this tapering has. So first I'll show you our standard 12 or 13 micron pitch and what the pattern for that looks like. So here's our central lobe, and our degenerate lobes appear at plus or minus 6 degrees, 6.8 degrees. So we're limited to a field of view of about 12 degrees total, which is not great. But when we start introducing this tapering, we can see those lobes move out on the side. So this is a 5 micron pitch, field of view of about 36 degrees, which is moving closer to what we want. And then we pushed ourselves to taper down to 4 microns, and we get back to our field of view of 45 degrees. Now, like I said, these are coupled with the same thermo-optic phase shifters, as we demonstrated before, that should get us the full range of steering that our device can do. We just don't have it isolated yet, so we can't show off those results. But hopefully the next time that I present this, and I don't know if it'll be to the exact same group, but to the next Frontiers group, I'll be able to show some better results of actually steering these arrays. I'll give a quick wrap-up slide of, we were able to demonstrate these thermally tunable integrated optical phased arrays, which require no 0-degree calibration. All that means is you can turn them on, not give them any power. You can put a laser through them, and they're still always going to aim at 0 degrees no matter what. We utilize some thermal isolation structures to mitigate interchannel crosstalk to maintain beam quality at large angles. We've coupled these arrays into phase-maintaining pitch-reducing structures, so those tapers, to get a increased maximum steering angle. And this design and these designs that we've shown here can be expanded to a large number of channels to achieve even higher beam quality and array performance. We also published a paper on this, which was pretty cool. I enjoyed getting to write that paper. If we have a few minutes, I'm just going to go really quickly through one other. This is kind of the fun one that we have of applications of the thermal isolation trench. If we've got,
yeah, that would be great. How long will that take, Dr. Bouchard?
I can get through it pretty quick. Probably, I can aim to go through in about 5 minutes on this.
Okay, great. Yes, please. Yeah, thank you.
Yep. Yeah, so we mentioned before, we can do these trench undercuts. We were trying to, the big part of this study, this was something one of my colleagues was working on, was studying how just overall efficient these thermo-optic phase shifters are on their own. We did some simulations to see where the heat goes in a smaller phase shifter and what that looks like. But when we were measuring these, we were pushing them up to higher and higher powers. And like I said, this doesn't really require much power to actually melt them. What we saw was they glow. They'll start like the filament for a light bulb. These things will just glow because they're getting so hot that they're emitting black body radiation. And it's really cool to see in person. You look at these little chips and you see like a small square of intensely bright, like orange light coming off of them. And what you get out of that is your waveguide itself is that you're heating up is emitting light, which can then be captured and sent down the waveguide to do spectroscopy on the chip, or it's a light source that we can actually use on the chip itself. I'm really looking for, we've got some more interesting photos here. We didn't include them. Well, that was just another quick application that we had here of, breaking these thermal pathways allow us to get to crazy high temperatures on the chip. We're pushing these things to failure quite frequently, and it's pretty neat work. I will wrap up by saying there are a lot of student opportunities down here at NRL. There is the NREIP, which is something you can do when you are an undergraduate student, but we also have the SSEP, STEM Student Employment Program, which is open to high school students. We've got some people actually that are in my group now that came to work at the lab starting in their freshman year of high school and have continued to work here all throughout undergrad and are now full-time employees. So if this is of interest to any of you, please go on. Here's the URL. Like I said, like Rudra said, this is going to be recorded, so I'm going to spend a few moments on this slide, but take pictures if you want. Check out this website, and if you do go to apply, reach out to me at my email. Let me know. Feel free to connect with me on LinkedIn.
I'm suggesting them to take a picture of this slide. Will that be okay?
Great. Yeah.
Please take a picture of this slide. You can see that information later. Okay. Thank you so much, Dr. Bouchard, for this very interesting and practical research. Now, some of the students have questions. Uh, Caleb, your question?
How does heating it change the phase? And also, if you want to angle it back, don't you need to wait for it to cool down again?
Okay. By the way, can that be hard, or like he has to
Yeah,
come
yeah, I
with
can
the
hear that.
front? Okay,
No,
good.
those are both really good questions. So how does heating it change the phase? So materials have what's called a thermo-optic coefficient, and that tells you at any specific wavelength, it tells you how much the phase or the refractive index of that material will change based on temperature. And you can then calculate, given a certain length of heated waveguide, how much the phase of your light will change based on the temperature that you apply to the waveguide. So different materials have different thermo-optic coefficients. Silicon has a relatively high one, so that's the waveguides that we used for these. It winds up with pretty efficient phase shifters. I mentioned before that we also work with silicon nitride, which does have a lower thermo-optic coefficient, but it can also be used for phase change. The other question about waiting for it to cool down, that's a really significant thing, and that's something that we worked on a little bit on this. We have some results, and we're formalizing them a little bit more to put into another paper. When you do this thermal isolation thing, you break that conduction pathway, which also slows down the steering of these arrays. So you can heat them up really quickly, you can get them up to really high temperatures, but there's really nowhere for that heat to go when you turn these things off. So based on experiments I've done in the lab, the non-isolated beam steerers will steer, to their maximum angle and back, and they'll do that at the rate of 10,000 times a second. They can go 0 to max just over and over again. When you start isolating them, they go down to by at least an order of magnitude to only being able to operate at 1 kilohertz or below. And this is a significant problem. This is something that we work a lot with when we're engineering these systems. We try to figure out what the maximum speed that something like this has to work at, and we have to sort of engineer our phase shifters. I will say, again, this is all thermo-optic, but there are other ways to change the phase of light going through a waveguide. One of them is by using an electro-optic material. This is a material that has an electro-optic coefficient, where if you give it an electric field, it'll change its index of refraction. Those work at gigahertz frequencies, so those can operate at a million times or tens of millions of times a second. Those materials are still under a lot of research. We're getting them put into conventional photonics fabs or foundries, so they're not really open for mass producibility like what we were looking at in this project, but it is something that we're looking into for the future.
Okay, thank you very much. We have another question here. Yeah.
Sure.
How do these things help you communicate? Or
How do they help?
What are they used for?
Yeah, so like I showed a little bit earlier on in the talk, we use these for, let me see if I can scroll on up. These are used for things like ship-to-ship communication, or for something this light, you could put it on possibly like a drone. It would be able to steer like a communication beam back to some ground station that's controlling it, or it'd be able to send information over that laser line that it's sending out. So the light that is coming through the optical phased array has some information encoded on it that we want to send to a ground station somewhere. That's typically what systems like this are used for, but they can also be used for there's a group out of MIT that publishes quite a lot that uses these beam steerers for doing augmented reality. So they're using it to steer a whole bunch of different pixels together to create augmented reality glasses. People also use these things for LiDAR systems. So like you see on like driverless cars, those large spinning LiDARs, they're trying to move those into non-mechanical devices. So they're using these like non-mechanical beam steers like OPAs to steer LiDAR beams around.
Well, how do you encode information in light?
Yeah. So you can use there's a lot of different properties that you can use to encode information on. People do it on like wavelength. You can send a whole bunch of different discrete wavelengths of light down the same waveguide, and they won't interfere with each other. And depending on the different wavelengths, how they're changing, you can get information stored on that. You can change the amplitude of the light and sort of do like almost like Morse code by flashing it on or off. You can change the phase of the light, and that can have information on it. It all depends on just what the person that you're communicating with is looking for information on.
Okay, thanks.
Yeah, totally. Oh. Did we lose Rudra?
Any other? Sorry. Any other questions? Oh yeah, there is another question.
Wondering for on like the I think
Could you please raise your voice like so?
it was for the photonics companies, like it was like a diagram you had of the companies you worked with, and there was
Yeah.
like a red question mark next to Intel. What is that like?
I think this might be slightly out of date when they were talking about bringing out the 300 millimeter. So basically, like this is more of whether or not Intel is doing their photonics on either a 300 millimeter process or a 200 millimeter process. I think they've now confirmed they do 300 millimeter fab. All that will change is the fidelity or the accuracy or minimum feature size that they're able to achieve. But Intel is using integrated photonics. Also, NVIDIA now has some of their really high-end, I think it's mostly targeted at like data centers. They've got cards that are coming out that have integrated photonic circuits co-packaged in them. So these circuits are starting to be seen like in practical devices.
All right, thank you.
Yep.
Any other questions? There might be some questions which I may not be able to answer. Like so, those kind of questions, please ask the question to the expert.
Yeah, and if questions come up later on and you ask Rudra, he can email them to me and I can get back to you later on. I will try to answer questions like that.
Great. I believe there is one question. Is that right? Yeah.
Do the side beams also communicate information? The boundary beams, does that pose a risk to because you said that the purpose is to sort of like narrow down the area where they can be intercepted? Do those side beams pose any threat to that interception? I was just wondering. You don't have to.
Yeah, that's a good consideration. That is definitely a problem. We are sending some of our information. Yeah, because so the information is encoded in all the light that comes off of these optical phased arrays. So if we're sending stuff out, where we think we're sending it, and then also 20 degrees on either side of where we're sending it, that's not a good thing. There's information that's just getting sent out to nowhere or to someone listening in. There's a lot less power in those side lobes. So like 95% of our power is in that central lobe, even though it looks like they're in those images that I showed, it looks like they're about the same brightness. Most of the power that we have coming through our device, let's see if I got a good one. Yeah, this is a good, most of the power that we're sending out is actually in the central lobe. The camera that we use for this has like a weird and kind of annoying auto gain feature where it tries to balance the intensities across them. But most of the power is here. So the power in those degenerate side lobes will, it'll dissipate sooner. So it won't propagate as far through the atmosphere, but it's a consideration that we have to think of. So obviously eliminating those side lobes by going to the smallest pitch possible is the ideal. Yep.
Okay. Thank you so much. Answering, Dr. Bouchard, answering all questions from the students and giving this fantastic presentation. So let's thank the speaker. Hey, what's that? Thank you. Thank you very much.